which is Luis Enrique Coronas, which is a PhD student at the University of Barcelona. He graduated in physics at the University of Valladolid and obtained his master's degree in computational multiscale modeling at the University of Barcelona and at the Polytechnic University of Catalonia. His PhD thesis, done under the supervision of Giancarlo Franzese, is on statistical physics applied to multiscale modeling of hydrated bio-nano interfaces, focusing on the developing efficient parallel Monte Carlo algorithms for water and hydrated proteins. So please, Luis.
Well, thank you for your presentation. Let me share the screen. Sorry, it's this one. Can you see the slides now?
No, not at the moment.
No, maybe.
Now, yes. Now, yes.
Okay. Thank you. So, well, I will thank you for the presentation. I would also like to thank the organizers for giving me the opportunity to participate at this series of seminars. I will talk about our research on water thermodynamics and its effects on biological interfaces. But first of all, I would like to acknowledge works by Valentino Bianco and Ivan Kolutza for their previous contribution to this research. And I also like to thank Fabio Sterpone, with which I'm currently working at Paris in France, where we are. The last part of this presentation will be devoted to the results obtained in this as preliminary results obtained within this collaboration. I will introduce this topic by recalling that water is an anomalous liquid. It is known more than 60 anomalies, among which we have structural, dynamic, and thermodynamic anomalies. These anomalies are more relevant at the supercooled region, where enthalpy and density fluctuations increase rather than decrease, as in argon-like fluids. The most known of these anomalies is the fact that at a solid state, the ice is lesser dense than the liquid water. But we are also interested in polyamorphism, which is the fact that water can form different amorphous states at extreme low temperatures, and which of these states is formed depends on the preparation route of the sample. This polymorphism is indicative of a possible liquid-to-liquid phase transition at the supercooled region. And in order to explain these anomalies, there have been 4 thermodynamics scenarios that has been hypothesized in theory, but their test in experiments is difficult, mainly due to the crystallization of large water samples. Experiments are usually performed under confinement conditions or for water monolayers. This is not this kind of confined water has different properties than the bulk. So maybe the conclusions we find from these experiments are not extrapolable to bulk water. And also simulations have succeeded in showing, at least for some models, the occurrence of the liquid-to-liquid phase transition. But as models, they are only represent water approximately. They can never reproduce, or we can be sure how accurately they reproduce water at some thermodynamic points. But this question about the origins of anomalies in water can be generalized because there are many other systems which are also anomalous liquids, and we can wonder if there is a common mechanism giving rise to anomalous behavior more general than just in water. We will restrict ourselves to the analysis of network-forming liquids, anomalous liquids, as water is one of them, which forms a network of hydrogen bond interactions. So in order to address this general question, we look for a coarse-grained model within the following desiderata. First, we want it to be analytically tractable. We want to extract the general conclusions about the model. A coarse-grained model with being analytically tractable, just to extract the general features about the model. We want it to have tunable parameters, as a set of parameters will define the behavior of a system, and one of these systems would probably correspond to a different anomalous liquid. And by tuning the parameters, we also are able to extract which is the role of each interaction into the total behavior of the system. We are also interested in performing simulations at the supercooled region, so we need to find algorithms being able to equilibrate the model at extreme cold conditions and for a wide range of pressures. Also, we are interested that these algorithms are able to simulate large-size systems for long-time simulations, as this is required for introducing into the model biological interfaces, as we will see in the last part of the presentation, and also to perform properly a finite size scaling analysis. The first attempt within this of finding these models is proposed by Sastry, De Benedetti, Shortino, and Stanley. They proposed this coarse-grained model for water, in which instead of coarse-graining, instead of performing spatially coarse-grain of the system, in which you pack different entities such as atoms or molecules into a bigger entity and describe the interaction of the system with effective potentials, they perform a coarse-grain over the degrees of freedom of these molecules. So they kept the molecular description and just reduced the degrees of freedom of the molecules to represent the hydrogen bond network. They start by partitioning the total volume of the system into a lattice, into a regular lattice, as we see in the left, each lattice containing at most one molecule. This is a coarse-grain of the positions of the molecule, and they only kept the average distance between two neighboring molecules, which is the radius of the cell R, as we see also in the right panel. To account for the hydrogen bond network, they introduced a set of bonding variables, in which which is defined here in the right. Here in the center molecule, we have 4 arrows, 4 bonding variables facing the 4 neighboring first neighboring cells, and this is done for every molecule. So there are also the bonding variable for the neighboring facing to the central molecule. And anytime these variables act like a POTS variable, which can take up to 6 different values. And anytime two of these bonding variables are in the same state, then a hydrogen bond is formed. The model also assumes that all density heterogeneities of the system arise from the presence of hydrogen bonds. So anytime a hydrogen bond is formed, they add a small amount of volume to the system, which is this BHP parameter in the central equation. So the total volume of the system can be described as a homogeneous contribution which is just the number of cells multiplied by the volume of the cell, plus this volume term coming from the presence of hydrogen bonds. Within this model, Sastrian co-workers were able to reproduce the anomalies of water without finding criticality at the supercooled region. So they show that it is not essential for a system for anomalous system to have critical behavior at the supercooled region. But this model doesn't take into account cooperativity of the system, or cooperativity of the hydrogen bond interaction, which is an essential feature of this interaction. Here we have in this example quantum mechanical calculations of the many-body expansion of the hydrogen bond interaction energy for two different water clusters. In the small water cluster, we see that many-body contributions up to 4-body terms are already relevant, but we also see that for a larger water cluster, they become even more relevant. So the larger the cluster, the water cluster is the more relevant are the contributions coming from many-body terms. This is why Franzese and Stanley decided to introduce a new term to the enthalpy in the Sastry model, which is this many-body term. They define a many-body bond or a cooperative bond as any time two bonding variables of the same molecule are in the same state. Now we have a model with 3 parameters, this J sigma controlling the hydrogen bond interaction, and also the VHV controlling the effect on pressure, which is the contribution to the volume from the hydrogen bonds. And this represents a wide variety of anomalous liquids, among which water is just a particular case for a certain choice of parameters. But the introduction of cooperativity into a system changes completely the situation in the Sastry model. Now, as we see here in this plot, this is mean field calculations for the Franzese-Stanley model. The Sastry model is a particular case in which there is no cooperativity, in which J sigma is equal to 0, and this corresponds to the x-axis in the red line in this diagram, which corresponds to the singularity-free scenario. But by introducing cooperativity to the system, we find that a liquid-to-liquid phase transition emerges at low temperature and high pressure, ending in a critical point at positive pressure. For larger increase of cooperativity, this critical point shifts to negative pressures, and for even larger cooperativity, the critical point crosses the liquid-to-gas spinodal, giving rise to the critical point free scenario, which are also consistent with the stability limit conjecture. So we find that by introducing cooperativity to the system, the model is able to reproduce all the 4 thermodynamic scenarios proposed for the origin of water anomalies. So we have this answer to the first question. It is the amount of cooperativity of the hydrogen bonds, which controls which of the proposed scenarios holds for a certain anomalous liquid. By estimates from experiments, from experimental results of the cooperative amount of hydrogen bond, Stockley and co-workers determined that the most probable parameters for water in the Franzese-Stanley model lied in this blue-shaped region corresponding to the liquid-to-liquid critical point scenario with positive critical pressure. Now, Valentino Bianco and Franzese fixed parameters, the parameters of the model, and studied its application to a water monolayer. In the phase diagram, they find two maxima for the response functions at different temperatures. At high temperature, the maxima of the response function corresponds to the formation of the hydrogen bond network, while at low temperature, it corresponds to the local rearrangement. For the rearrangement of the hydrogen bond interaction due to the cooperative effect. This result can explain or allows us to clarify the origin of the two dynamic crossovers, which is observed in water monolayer experiments. Here we have two examples in water layer on crystalline ice and also in protein hydration water. So these results can be explained with atomistic models, which are parameterized for bulk water, as they only observe one maxima for the response function. So this is also a success for this model that can clarify the origin of these two dynamic crossovers and relate them to the formation of the hydrogen bond network and the cooperativity effect. But as I said at the beginning of the presentation, we know that dimensionality plays a relevant role, as we know that water monolayer doesn't behave as a bulk water. So this is where I started my PhD. We were working on extending the Franzese-Stanley model to 3 dimensions and answer the question of how does the dimensionality modify or affect these results. We start with the Franzese-Stanley model in 3 dimensions, and I highlight here in the center the ambient conditions. And here we observe no qualitative difference between 2 dimensions and 3 dimensions. But we can it helps. These results are easier to adjust to experimental data on bulk water, although I'm not showing these results at these slides. But more interesting than that is the fact that at high pressure or ambient or larger pressure and low temperatures, we find that the high temperature maxima of the response function merge to the low temperature maxima of the response function, and here we only observe one maxima, as in atomistic simulations. So this 3-dimensional model is consistent with atomistic simulations where we only observe one maxima for the response function. This effect is clearer for a larger cooperativity that shifts this line of low temperature maxima to higher temperatures. So this merge occurs even at lower pressure and higher temperatures. Next, we study the critical region. We have tested the Stokely result, and we find that all of the scenarios can be reproduced in 3 dimensions with the model, although also these results are not presented here. Now, for this set of parameters, we find this liquid-to-liquid critical point at positive pressure, but it's still lacking a finite size scaling analysis to better locate it in the phase diagram. We have proven its occurrence with umbrella sampling calculations of the free energy barrier. At low pressure, we find only one that system is only in one state, but for intermediate pressure 0.3 in our internal units, we find coexistence between 2 states with a barrier of the order of 10 kVt, and for higher pressure, this barrier increases. So this is consistent with the occurrence of a liquid-to-liquid phase transition ending in a critical point. And it's a matter of performing the finite size scaling to better locate this critical point in the phase diagram. Now we move to the second part of the presentation, which is devoted to our results in iterated systems. Atomistic models are only suitable for small size systems and short time simulations. And they are computationally expensive to give general answers to questions that we have mentioned before, which is the general mechanism for protein unfolding, which is the role of the solvent in protein design. So we ask if we can apply the Franzese-Stanley approach to study the role of the solvent in processes involving nanobiological interfaces. And this slide shows results in 2 dimensions, which works pretty well. They were performed by Valentino Bianco, Christoph Delago, Ivan Kolutza, and co-workers. And they studied a wide variety of phenomena involving iterated systems, including protein folding, protein design, and protein aggregation. In protein folding, the model is able to reproduce the elliptical shape of the stability region in the phase diagram, as predicted in theory, and they show which is that it is the role of the solvent, which is the role of the solvent in the unfolding processes. The most intriguing case is cold unfolding, in which by lowering temperature the protein unfolds, and the model explains this phenomenon as lowering of the total energy of the system by forming more hydrogen bonds at the iteration shell. So the global energy of the system decreases by forming these hydrogen bonds, and then the protein unfolds to lower this total energy. In the case of protein design, we find that the solvent with the model, they are able to mimic natural selection of proteins, and it is and they find that the role of the solvent is that for proteins designed at high temperature, they have a wider stability region in the phase diagram. They also compare these results with those obtained in implicit solvent, with an implicit solvent design, and they find that they cannot reproduce with implicit solvent this behavior for the system. In the case of protein aggregation, they increase the protein concentration of the system, and they find that the proteins first unfold and then aggregate. These interactions are water mediated, and this is relevant for studying the origins of neurodegenerative diseases, as they are triggered by the formation of aggregates of peptides. But again, all of these results are obtained in 2 dimensions, and we wonder if in 3 dimensions they are still valid. So in this context, we started a collaboration with Fabio Sterpone in Paris, where in their research group they apply the OPEP coarse-grained model, which represents amino acids as one bit for the side chain and the backbone at atomistic level. And they, in this example, we are mapping one of their configurations. In this case, we have A1, A2, A3 fragment of the von Willebrand factor. This is a protein present in blood, and its misfunctionality affects the formation, is related to the development of thrombosis. And we start by mapping this protein configuration into our coarse-grained lattice model, and we equilibrate the water of this system around this configuration of proteins. We find in this case the protein is under external force field, and they fluctuate between these three kind of configurations. One in which the three proteins are attached to each other. In yellow, in red, we have one separated and two of them attached. And in green, we have that the three proteins are separated. We find that water is sensitive to these protein conformations, and we find a different solvation free energy depending on the protein configuration. This clarifies the role of water in the behavior of this system, as it acts like a guiding force that tends to separate the proteins in order to minimize the solvation free energy. So, as a conclusion, I would like to highlight that the Franzese-Stanley model clarifies the role of hydrogen bond cooperativity, and it is suitable for analytic calculations and Monte Carlo simulations at extreme conditions. We have studied the effect of dimensionality. We find in 2 dimensions density and cooperativity fluctuations decouple, while in 3 dimensions they merge, which is consistent with atomistic models for bulk water. And in the case of 2 dimensions, it helps explaining experimental results on water dynamic crossovers. In both dimensionalities, we find the fluctuations are critical if there is cooperativity. In the case of the study of proteins in explicit water, we find that in 2 dimensions, the model clarifies the role of water in a wide variety of phenomena, including folding, design, and aggregation. And in 3 dimensions, it is suitable to calculations of free energy of large protein systems. So thank you for your attention.
Thank you, Luis, for the presentation. Are there questions or comments? I have one question concerning, it seems to me that you did a kind of, let's say, extension or generalization to 3Ds or models that were highly investigated in 2Ds or in constrained geometry, right?
Right, yes.
And in this generalization, it was just, the problem was just to, let's say, extend it to another dimension, or you had also to take into account, let's say, some other details of the model generalization?
Yes, there were many things that we had to take into account. We find, sorry, I think I will share again the screen. We find that the first point we have to take into account is that in 2 dimensions you have four nearest neighboring cells, but in 3 dimensions you have 6. Yes. This increases on the one hand increases the total amount of entropy of the system, because you have more bonding variables and more accessible configurations. But there is also a restriction that hydrogen bonds, so water molecules can form only up to 4 hydrogen bonds. So in 2 dimensions, this is not a problem, because you only have four neighbors. But in 3 dimensions, as you have 6 molecules, you have to take care of with which molecule a water molecule is forming a hydrogen bond and with which not, because we start finding we just take care of not allowing a water molecule form more than 4 hydrogen bonds. But we find that by doing this at low pressures, as the formation of the hydrogen bonds is more gradual, you find that you ended in a situation at low temperatures in which there were many molecules had already formed the 4 hydrogen bonds, and there were some molecules that couldn't form no more hydrogen bonds because all of its neighbors had already 4. So there was you couldn't saturate the hydrogen bond network, as there were some some molecules that couldn't form this hydrogen bond. This was the most intriguing part of the generalization, and we developed an algorithm to like a super. It was like a super. I think I have in a slide here at the end. Like this, we introduced a super partition that allowing only among the 6 molecules, it forbids forming 2 of these bonds and allows forming the other 2. And this is done at the same time for all of the molecules, so they can always form 4 hydrogen bonds. This was the most intriguing part of this generalization.
Okay, thank you. Other questions or comments? So if not, perhaps we can thank again the speakers of this section, of this December session. And this is the last session of the year. So next one will be in the new year. It will be the 10th of January. So all the best for all of you, and have a good rest and vacation if you have time for that. Okay.
Thank you.
Bye. Ciao.